Good morning. Can you see my screen? Hello? Hello? Am I
Yes, sir.
audible? And you
Yes, sir.
can see my screen? Yeah. Okay. Okay. So let me start talking. Good morning. Good morning, everybody, and Happy New Year. So in this class, I will be teaching electric drives. Um, this course is divided between me and Professor Shao. Professor Shao will take over after maybe 6-7 weeks of lecture. So electric drives is essentially how an electrical system uh, reacts with the mechanical system. Okay, so electrical system reacts with mechanical system. We have already got an idea, little bit of an idea, or some, not little bit, a substantial idea. Substantial idea is when you have studied electrical machines, because machines is nothing but an electromechanical energy converter. Electrical energy in, mechanical energy out, or mechanical energy in, electrical energy out. That is what this electrical machines does. So what is extra here? Here the extra part of this course is uh, a kind of processing. When we are getting the electrical energy, you understand that we are either giving electrical energy or taking out the electrical energy. So basic thing is, basic block diagram, if I look at it, this is electrical energy, and this is mechanical energy. Mechanical energy. Electrical energy comes in the form of essentially voltage and current. Mechanical energy represents itself, shows itself in the form of torque and speed. Torque and speed. That is how mechanical energy, mechanical power, whether I'm writing energy, essentially I'm talking in terms of power. V into I is a power expression. Torque into speed is a power expression. Energy comes in the form of time. So almost like integration. Integration of power is energy. So this is what is electrical machine does. Electrical machine does. It comes in form of, you already know, AC machine and DC machine, depending upon the nature of the input of the electrical engine energy. Input or output, I may sometimes say input, that is the convention, thinking always in terms of a motor. Motor is electrical energy in, mechanical energy out. But when mechanical energy in and electrical energy out, we call it generator. Okay, so just a electrical machine is a bidirectional energy transfer device. It doesn't have any specific choice that it will only transfer energy in one direction. It is completely bidirectional device. It depends upon application. It can be either used as a generator or a motor. So this electrical machine we have studied in our earlier class, and it has come out in the form of DC machine and AC machine in general. So in general, DC and AC machine also gets divided into two parts, which are called induction machine and synchronous machine. Okay, it shows up in these two forms. There are some modern electrical machines, we may even call it electronic machines, that are nowadays coming up, which are completely dependent on electronic method of giving them power. You understand what is the difference? Electrical method of giving them power. By the way, if you have any doubt, please ask me. No, there is no, you can stop me and ask me. Okay, sometimes I may not be, actually I'm looking at a screen, I'm not seeing your faces, so it is difficult for me to guess what exactly you are thinking, or whether you are able to grasp it or not. So sometimes I stop talking to you directly, but you understand the reason for that, because I'm looking at a screen on my screen and talking. Your expressions are not apparent to me, so I sometimes talk interacting directly with you, but you please stop me. There is no it is more like a discussion. This must be your 4th year course, so it must be something like discussion for you. So let us see whether we can learn anything from here or not. Take something about the electrical engineering inside you. So that's why you are allowed to stop me. So what I was saying is electrical, I am making a little bit of difference between electrical machine and as if electronic machine. I will say that, because it requires a power supply that has to be electronically produced. What do you mean by electronically produced? Is electrical energy already, as on this thing, is available at our terminals. We have 415 volt 3-phase AC supply, or 220 volt DC supply, 220 volt AC supply, single phase AC supply, etc., etc. In some other cases, we also get, for example, in the lab, we may get a 220 volt DC supply. Okay, electronic supply is saying that the electronic and most of the machines, DC machines will work from this, AC machines will work from this. Okay, 220 volt single phase AC supply, which AC machine works? It is our fan. It is a single phase induction machine that works from it. Okay, so you don't need to do much about it for the time being. Take it like that. At least machine will rotate. But with this supply, with this kind of supply, you cannot make an electronic machine rotate. You have to process that supply first and generate a supply that is suitable for the machine, right? So for the machine, you need to first process it and generate it. So that's why I'm slightly inclined to call them an electronic machine, just to make a distinction between them. And the names of that machines are also coming out, are also becoming more and more popular. BLDC is one of them. It is called brushless DC machine. Though its name is like brushless DC machine, it is close to a, since it is brushless, this thing, it is more close to an AC machine, more closely to an AC machine. Okay, so in modern times, there is another change that is happening in the machine structure. So that machine structure is changing in the sense that you already know, I hope you know, that synchronous machine, think about synchronous machine. Synchronous machine, what is there? Synchronous machine, if I think simply, 3-phase synchronous machine, if I think simply, there are 3 coils, stator coils, and a coil which is given a DC supply in the rotor. This is the stator part of it. This is the stator part of it, which comes out as a terminal to the output. Okay, and this is also another supply you give to the rotor part of it. Rotor also has a coil. Rotor has a coil, and they are wound on the same magnetic structure. And then magnetic structure means they link each other, stator and rotor. Obviously, in a machine there is one stator and one rotor, right? That not like transformer. Transformer has no rotational part. Machine has a rotational part. So synchronous machine has this kind of rotational part. Three stator coils in the stator and one rotor coil in the rotor, and the rotor fellow by definition is rotating. So therefore a DC supply, and it is given a DC supply. So field is created by the DC supply, and you may brush up these things a little bit, and therefore the rotating magnetic field will be created because the rotor is rotating. And in a rotating magnetic field, if there is a stationary coil, then that will induce voltage by our well-known Faraday's law, V is equal to N d phi by dt. That's what is happening. So what I was telling is that this new kind of machines that are coming up, which I am trying to give it a name, electronic machine, just to distinguish them from the conventional electrical machines, has sometimes have permanent magnet in the rotor. The conventional electrical machines, the rotor is still the same material. Still material means it is still made of iron core, maybe cold rolled grade oriented variety. So it is still made of iron core, that means magnetic material. Whereas in the recent machines, they are putting in the rotor part in order to improve efficiency and reduce many kinds of complications. Complication means only connection complications, no theoretical complications. So sometimes this rotor is nowadays going in these machines into permanent magnet material. Permanent magnet material. Okay, so apparently you don't have then two extra terminals because rotor is already supplied by a permanent magnet material. So with these two new kind of machines coming up, one is BLDC with permanent magnet and another is synchronous machine with permanent magnet. So we call it BLDC, brushless DC machine, and PMSM machine, PMSM machines. Permanent magnet synchronous. Synchronous machine, right? So these two are more famous electronic machines. You cannot run them by giving them any supply, just giving them any supply that is available from the utility grid. So from utility grid, they cannot be run. From utility grid supply these machines means BLDC and PMSM can be run. So this is the issue of this. So you are seeing that electronics is entering into machines. Electronics is entering into the machines the way the machine requires its supply. That means what we are understanding is it's just not necessary somehow to give some energy source, somehow to connect an energy source. What energy source we are connecting, in what form these energy sources are available is also important. And therefore, we are coming into the realm of power electronics, power converters. The power converter's basic job is to modify the available source to the form that would be required by the machine. That is the requirement, because machine to mechanical system interaction has already happened. but the available source supply, which is mostly available from the grid in the form of either 220-volt single phase or in the form and 50 Hz. The frequency is frozen. So 220-volt 50 Hz or 415-volt 50 Hz, 3-phase. Okay. So those things have now to be suitably modified. Okay, in order to cater to the requirement of the machine and its more versatile operation. For BLDC and PMSM machine, there is no question. You have to give it because that is the way. You cannot give a sinusoidal supply to a BLDC machine, sinusoidal voltage supply to a BLDC. Okay, you cannot just like that give anything to the PMSM machine. Okay, so but even though I could have given such supply to the conventional induction machine and conventional synchronous machine, where the rotor is not permanent magnet type. In fact, you know the induction machine rotor. Induction machine rotor, I remind you, have two kinds of rotors. One is called squirrel cage machine. Because what? Because the rotors are taking the structure of a squirrel cage conductors, and that is short circuited, or it is in the structure of a wound rotor machine or slip ring machine, which is exactly the same structure as the stator coils, 3-phase coil structure in the both in the stator and rotor. However, the rotor would have, therefore the rotor will have to be given supply externally, just like stator. Okay, the stator coils have to be given supply as well as the rotor coil will have to be given supply in case of a wound rotor machine. So in that case, that when you are giving a supply to the wound rotor machine, since it is in the rotor, we require a special mechanical arrangement called slip ring. So through slip ring, the supply that is stationary gets connected to the coils of the rotor who are not stationary, who are rotating. So this kind of rotating contact, the name of that rotating contact is called slip ring, right? So we have talked about that in our this thing. I am probably you have slightly forgotten some of the things I am trying to bring in. So therefore, electric drives is essentially saying how do we do these modifications so that we do better job, either better job with the machine, with the conventional machine, or do the essential job for electronic machines. Electronic machines are AC, permanent magnet synchronous machines and brushless DC machines. Okay, both are essentially AC machines. Don't get confused by the name brushless DC. When you remove the brushes from a DC machine, it actually becomes an AC machine. Actually, everything is an AC machine. Why? Because every machine ultimately works on Faraday's law, and Faraday's law is saying V is equal to N d phi by dt. So d phi by dt implies that there is a time variation. So time variation implies that internally everything is an AC. There is no question of DC. Brushless DC, with the actual DC machine is nothing but a rectifier, which rectifies the internally induced voltages in the coils, rectifies it and gives it to the terminal. Earlier time there was no diode rectifier, so it was a mechanical rectifier. So commutator and brush is exactly acting like a mechanical rectifier. People were brilliant that time also. They understood, even though semiconductor was not available, they made a mechanical rectifier. It complicated the machine immensely, but job is done. And initial development of different industries were reliant on the DC machines for quite some time. Our old, if you go to our old steel plants, Bokaro, Bhilai, you will still see that it is running on old DC machines. It is still running. People prefer it. DC machine is easier to control. Many other advantages are also there, but its only disadvantage is that brushes and commutators, which require maintenance, etc., etc. So over a period of time, people thought whatever job is done by the DC machine will do to the AC machine, right? So that way the induction machine and synchronous machine came into thing. And the induction machine, it was found that compared to the induction machine, synchronous machine is slightly better efficiency. So at the high power end, when you require very high power, you will go for synchronous machine. But when it is low power, then you will go for squirrel cage induction machine because of simpler construction. It is a brilliant construction. It doesn't have any rotor terminals. Rotor terminals short circuited, and short circuited means we get scared that, oh, short circuit means a lot of current will go. The brilliance is in that they understood that the current will not be high because the induced voltage, the machine operates with such a principle that induced voltage in the coil itself is low. So V by Z, if you look at it, the voltage itself is low. Voltage itself is a factor multiplied by the synchronous speed, right? So if the stator voltage is V, rotor voltage will be SV, where S is very low. S is about 2%, 3%. So the voltage being low, even if you short circuit it, there will be not much current. It is limited by the coil's leakage, inductance, and the resistance. No issue. So this machine became popular because of its constructional advantages over a period of time in industry, in where you don't require. That's why in our lab, in our small applications, most of the machines are induction machines. So up to 100 kilowatt, nobody will be using any synchronous machine. Synchronous machine may be used at the high power end, maybe greater than 500 kilowatt, etc. So that range, okay. But synchronous machine is used in another niche applications, very important applications. They are called servo applications. Servo applications are those applications where position control becomes important. By the way, all the machines that we'll be talking about from now onwards, we expect them to do speed control or position control. Position control. These are the application requirements. Application requirements. So these are application that you want the machine to run at a certain speed. Can you think of an app? Why do you want to run the machine at a certain speed and you want to change the speed as well? Suppose there is a conveyor where things are going from one end to another end. So the conveyor, sometimes you want to, depending upon, suppose it's a conveyor which is carrying coal to a power plant, right? So the conveyor may, sometimes you want the conveyor to run at some speed, okay, when it is in the peak hours, the load is maximum, the generator has to produce lot of power, then that conveyor which is carrying coal, I'm talking about traditional things, conveyor must run at higher speed than compared to the time when the generator is running under slightly less load. So there is a requirement of a speed control, okay. Position control, you already know, the missile, etc., different kind of guidance system, radar, where you want to move something, antenna, focusing from one direction to another direction. There are various kind of position control and sophisticated applications are there. In such kind of sophisticated position control applications, we require something which we know, define it as AC servo machine. AC servo machine. Servo, whenever you see a machine is said servo machine, you understand that they are not for industrial uses. They are mostly for position control kind of applications. Okay, so those machines are mainly synchronous machines. Synchronous machine. So most in industrial applications nowadays are AC machines, unless it is very high power, and at high power we have synchronous machines in the megawatt range. In the megawatt range we have synchronous machines. For and applications, new applications. In the new applications area, BLDC is entering. BLDC has is taking the area of our electric car. Electric car, the motor will be BLDC machine. Sometimes BLDC machine, sometimes synchronous PMSM machine, sometimes induction machine. All three machines are competing with each other. We already get some update that this company is making with using permanent magnet synchronous machine, which has better efficiency. Another information we'll get is that people are making it with induction machine. It seems Tesla has made their that electric vehicle with induction machine. It seems they have chosen induction machine, but they have used copper in the rotor. The squirrel cage of that is made up of copper, so that the efficiency becomes better. Normally, you will see that in the lab or somewhere, people use aluminum conductors. In order to cut cost, they use aluminum conductors. But you see that what I'm trying to say is that without any much bias, we should have an open mind in an application to choose the machine that we require. It depends upon many things. It depends upon cost, it depends upon availability of the material. Permanent magnet has little bit problem because permanent magnet is a material that is available only in some special parts of the earth. It seems China has lot of stock of permanent magnet material, so they may one time dictate terms. So probably Tesla is trying to avoid that and trying to do all their development on induction machines. So it is the techno commercial. A lot of factors come in, and what I'm telling here is not a gospel truth. I'm just trying to tell you the aspects that we need to consider when we choose a machine for an application, and the applications are essentially two types: speed control and position control. You may want to run the application at a certain speed and at a place something at a certain position. Right. However, any machine is ultimately defined by its characteristics of torque versus speed, or in more generally, a machine is a torque generator. What is the essential thing that we are expecting from a machine? We are expecting that it will give certain torque that I require. That is what is the core thing that I am deriving. Externally, from the application point, it may look like a speed, but eventually from the machine, when it comes to the machine, what we are expecting from the machine is a torque, that you give me this torque. And if I am linking with this, I will say at this speed you give me this torque, at that speed you give me that torque. So torque is an independent variable. Torque doesn't depend upon speed. Many people have got this misunderstanding that torque is dependent on speed. Machine torque is not dependent on speed. I can generate torque at 10 rpm. I can generate the same torque at 100 rpm. I should have no problem. So in order to develop this flexibility, also that to generate torque, because essentially motor is capable of giving torque. Torque is TD, torque developed by the machine, torque developed by a machine. And you already know that the torque expression is essentially what? Flux of the machine and current of the machine. I'm not here defining too precisely. This current, with all sorts of applications, as assumptions, you can, this phi is the magnetizing flux, the flux that magnetizes the core, and I is the current in the rotor coil. So this general definition, with this general definition, I can say that the torque, any machine is a torque generator, nothing other than torque generator. Machine doesn't understand what speed it is running. It is dictated by the external world. External world will say that I want to run, let us say machine is running at, let us understand it very simply. Let us say machine is running at 200 rpm and it is generating a torque of 10 Newton meter. Now you say I want to run the machine at 500 rpm. Okay, so what will be the initial thing? Initial thing will be the machine will get a command that it has to speed up. So how does it speed up? It speeds up by this expression, J d omega by dt is equal to developed torque minus load torque. So when it was running at 200 rpm, it had developed the torque corresponding to 10 Newton meter. That's what I said. That was the steady state. So it was in one steady state where the speed was 200 rpm and it had developed a torque of 10 Newton meter. It equated with the torque of the load torque. That's why there was no acceleration or deceleration. D omega by dt was 0. This was one steady state. We call it steady state. Now, new information has come to the machine that it must now go to 500 rpm. So what is the thing it is happening? If it will have a control loop that will compare the speed reference, which has become from 200 to 500, and actual speed is at that moment initially is 200 rpm. So there is an error. So from that error, you will develop a torque reference. So that means you will say that now I want to go to a torque in the transient state. I want to go to a torque that is higher, right? I want to do it, that they will decide. So let us say initially 10 nanometer Newton meter. So now let us say you want to go to a 20 Newton meter. So that 20 Newton meter implies that flux cannot be changed. So machine will try to change the current. So since the requirement has become 20 Newton meter, why the requirement has come? Because there is a need to change the speed. So during the transient state, when the speed is changing from 200 rpm and going towards 500 rpm, during that process, let us say the current has to become double. Earlier, let us say current was 20 ampere when it was developing a torque of 10 nanometer. Now the current would become 40 ampere. It will become 40 ampere because it is developing a torque of 20 nanometer, right? Flux is unchanged. Why flux is unchanged? Why? Because the product wise it is torque. So why flux is unchanged? Because we cannot afford the magnetic material to saturate. So once you have designed a machine, your cross-sectional area of the iron core is decided. So therefore flux is decided. You cannot change it again. So this 40 ampere current, it develops higher torque, and therefore this is greater than T load torque. Load torque is, let us say, still at equal to 10 nanometer. So this is being positive. J d omega by dt then is positive. So which means that the speed will go up and go up and go up till it reaches the speed of 400 till it reaches the speed of this thing. What I said, how much? 500 rpm. So it has reached that speed, and at that moment it is still trying to give more torque. But then what happens? It tries to overshoot it. The moment it overshoots it, your control system will say that no, you have overshoot the limit, the desired speed limit. You have gone beyond. I only asked you to go up to 500 rpm, but you have gone beyond. Stop it. So stop it means what it will do? If the speed has gone up, a torque will be developed that is less than that. So let us say it has developed a torque of negative torque. That is also possible. It can produce a zero torque or a negative torque. So when it produces negative torque, both TD and TL are negative, then it will decelerate. So this process will continue, accelerate, decelerate, accelerate, decelerate. But however, it will ultimately the speed. Suppose you had given a reference like this, and the actual speed, it will go like this. First in integration, it will go up and then oscillate, and then ultimately it will come down to this. So this will be the new speed. This was 200 rpm and rpm, and this is 500 rpm. It will go like that. The speed, this is omega, it will go like that, and it will eventually settle down. In between, torque will change, plus minus, whatever it is. So at the core level, your adjusting criteria is torque in the machine level. Okay, the controller tells you what torque you require from the machine at a particular instant. Under steady d omega by dt. So therefore Td is equal to TL. But when it is under transient state, or we call it dynamic state, Td may be greater than TL. When you that is the simple basic operation of this electromechanical system. Electrical system's job is to produce torque. Electrical system, how does it produce torque? It produces by a product. Product of what? Flux and current. So flux of the machine and the current of the machine interact. Maybe there is some angle between them. Then you put that angle into it, sine delta angle. Delta is the angle between the flux and current. Then you put it sine delta angle. So this will be producing a torque, right? So don't bring any other complication. Your mind should be extremely clear that there is no other complication here. I should only focus on flux. I should only focus on current, nothing else, and that is the torque. What is speed? Speed is a second mechanical stuff. Speed is decided by J d omega by dt is equal to Td minus TL, right? If I just say the machine is now running at 10 Newton meter, torque is 10, I cannot, this doesn't give me an automatic information about the speed. I don't know. It may be 10 Newton meter during acceleration. It may be 10 Newton meter during steady state. I don't know what is happening. I don't know anything about the speed. So speed information has to be separately provided to you. So when you know both speed and torque, then you know what is the power. Torque into speed is equal to the power that is consumed by the machine, and that must be given by the supply system, right? So the electric drive's job is to adjust this torque dynamically and under steady. Obviously, if something adjusts it under dynamically, it will adjust it under steady state. So conceptually and electrical electric drive systems, then we can think of it like that. This is what we call at power converter. Okay, then we have, that means this is the basic utility grid. Utility grid from which power is available. It's a generic way I'm talking about. It may be AC, DC, anything. This is the power converter. So from the power converter, it goes to the machines, electrical machine, electrical machine, and from machine it will go to the mechanical system. Mechanical system. Mechanical system. So this is what is the electrical machine doing? It is doing electromechanical energy conversion. Electromechanical energy conversion. This is what is doing. So what is power converter doing? Power converter is processing electrical energy. Energy here is also electrical. Here also is electrical. Right? Electrical means voltage current. This is also voltage current. Okay. So, but at the machine output, we have given torque. We have produced omega torque. This is the let me say that it is mechanical first. Let me write it mechanical first. Mechanical first. This part is mechanical. Now this is reflected in the form of torque and speed. Torque and speed. This way it is written. Then mechanical system. Mechanical system has the moment of inertia J, characteristic by J, and that will develop based on the torque, it will develop the speed, and this is the way the interaction will be continuing. So you see that we don't have anything. Electrical drive system is essentially relying on power converter. It is the most focused thing is the power converter, because it is converting the energy into one form to another to have a better system operation in terms of efficiency, in terms of versatility into speed, whatever we want to extract from the mechanical system, overall system, we should be able to achieve that. And I will show you how we get benefited by this sort of things. So our electric drive systems will do this, but we will also consider the electrical machines part a little bit, because without understanding the electrical machine, the power converter cannot produce the required V and required I, if that would be required by the electrical machine. So power converter has its basic job is to take electrical energy from the grid and give it to the machine terminal in the form the machine terminal wants it, at the level of voltage it wants it, at the level of frequency it wants it. So that is the job. This is the essential job. So it is doing, that's what we call it, power processing. This is what is called, it does power, not signal processing, it is doing power processing. So in the power processing, our concern is that efficiency of the power processing should be very close to equal to 1. So that is what its job. It is in itself, it is not consuming any energy. You see, the electrical machine also has a very reasonably good efficiency. So power is actually, so that the entire thing, that the power that you are taking from the grid is going to the mechanical system without much loss. So we want to have this transfer from the utility grid to the mechanical system. Mechanical system is connected to the electrical system by means of a thing called shaft. You already know that shaft. You have seen in the lab what is a shaft. So utility grid gets, ultimately electrical machine is connected to the interface to the mechanical system through a shaft. Okay, this mechanical systems example may be a pump, a fan, etc. Pump, oblique, a fan, this kind of stuff. Okay, and our drives, electric drives, is concerned with this type of thing. So power conversion and electrical and the properties of the electrical machine and the characteristics of the electrical machine, that is where we will be focusing, and most of the focus is on power converters, because electrical machine will simply understand that, we'll take it a simple model that electrical machine just requires a torque, and we will be giving that torque in the way that electrical machine has less transients. We should not give it in such a way. For example, I will give you easy example. The torque, I said, is flux into current, right? So when the machine is demanding a torque, what do? I just have to see the difficulty. I just have to increase the current without increasing flux, because increasing flux will make it saturated. So I have to have a control system, or I have to give such a voltage at such a frequency such that the flux is unchanged, but current is changed. In order to adjust to the torque, I must not change the flux. See the difficulty? Because flux is proportional to the voltage level, integration of voltage. So while doing so, I must give such a voltage for such a duration that flux doesn't change, but the current in the machine I am able to adjust. So this is why the difficulty in the power converter comes. In the power converter is therefore assisted by a control system, which always takes care of the machine's condition. Machine's conditions are dictated by the flux condition and the current condition. So it is always measuring the flux condition and the current condition of the machine. And in order to produce any change, the change has to come from power converter. The change has to come from the power converter, because it has to process the voltage that it has received from the utility grid. and give it in a form. Because the utility gauge is a frozen system. I cannot directly give and expect that the flux of the machine will remain unchanged and the current will change. When I need to change the torque, when I need to change the torque, I need to change the current, not flux. So this is where the difficulty comes, and this is where the power converter's job comes. So it is very critical. Power converter has to do a very critical job in this situation. And during this job, it has to maintain that its processing efficiency is equal to 1. It doesn't lose anything, energy inside it. It doesn't do any processing using resistive elements, right? It has also the requirement of producing good dynamic performance. That means the torque, when I change, I should be able to change the torque immediately, because you quickly see that it is flux into current. So can I change the current as soon as possible without much delay? Because the lesser the delay, the more quickly the speed of the system will get affected by it. More quickly. That is what we want. And more precisely. In a servo application, we want precision also. Because servo application is saying you just position the radar at that angle. Okay? So it will be having the requirement of a precision as well. So this kind of thing, speed control and the precision, and the speed control and the position control, they ultimately boil down to a torque control and ultimately boil down to a current control without changing the flux. So externally it may look like speed oblique position. This control ultimately in the machine level becomes torque control. Very high dynamic torque control. And this torque control, when you have to execute through your power converter, you must see that it boils down to current control, I control. So everything is essentially I control without changing the flux, without changing the flux. That is what is the requirement of a drive system in essence. Why not flux? I repeat it, the flux change will saturate the machine. So we cannot afford to change the flux. Okay? People externally may say that you change speed. So what? We change speed means how do I change speed? By changing torque. How do I change torque? By changing current only, keeping the flux constant. So we have to generate a kind of voltage and frequency at the terminal, because it's a voltage source, mostly voltage or frequency or current or frequency. Sorry, I will come to that. There are two variations. One, just like our Thevenin theorem and Norton theorem, duality is there. You can either do it using a voltage source or using a current source. So when you are using a voltage source, you change voltage and frequency, and if it is a current source, you change current and frequency. If these two ways, which are dual, you can eventually handle the torque of the machine. We will understand this. So when we change voltage and frequency, we call it voltage source inverter. And when you change current and frequency, we call it current source inverter. Right? So these are the essence. This voltage is not, therefore by definition this voltage is not equal to the grid voltage, not equal to the V grid. Grid means the supply. This frequency is not equal to V supply. Supply frequency is always frozen at 50 Hz. Grid voltage, let us say, is always frozen at 415 volt RMS. Okay, we have to dynamically means as a function of time produce such a voltage and frequency that we change torque without adjusting it, without any variation in the machine's flux level, its saturation level, its magnetizing current level. We cannot afford to change. So when we do that, we will be able to extract the dynamic performance, better dynamic performance on the machine. So our performance is judged by this kind of dynamic performance of the machine, not only steady state, performance, meaning that not only that it should reach the torque that we desire and the speed we desire. But with what transients it is reaching it? Is it reaching it very fast? Is it reaching with without much overshoot? Is the control system stable? Is it oscillating? All those issues will be judged in electric drive systems. Electric system, good or bad, will be judged by this kind of performance criteria. So performance criteria wise, if I want to remember and write it, we have to think that dynamics and steady state performance. Steady state performance. That means steady state performance is steady state error, given by the steady state error. Which steady state error? For example, position error. Position error. And this dynamic performance is given by the speed of response. Speed of response, or trees of transient response. Transient response. And stability. The currents and voltages should not stability. Stability situations of the will be determined, and from the external point of view we should have efficiency criteria. Efficiency is equal to 1. So these two things are heavily dependent on the control system, and this is dependent on the power converter structure, power converter topology. Okay, so overall we are trying to match the source and the machine, source voltage and the machine voltage. For example, if the machine voltage in high power level is higher voltage required, then we have to decide a power converter structure that provides higher voltage. So this way we have to match it. Basic job is to match the source and the load, the source and the source voltage with the machine terminal voltage. That is what a power converter will be doing. And while doing so, it has to look into the control system requirements and the power converter topology. Power converter topology is simultaneously doing the matching the voltage, matching the source voltage to the machine supply, machine voltage is matching the source voltage to the machine voltage, and while doing so it can only do by a power converter topology. And the easiest way of matching the source voltage and this voltage is AC to DC or AC to AC, so on and so forth. So while doing so, it has to see that the efficiency is very nearly equal to 1, as well as it has to match two important aspects of the control system, that it will be the steady state performance, steady state position performance, either steady state position performance or steady state speed performance. These are the external requirement, that it should be running at this speed or that speed. And the dynamic performance, what is the speed of the transient response, we have to see that, and we have to see that the system is overall stable. So control system also is a part of electric drives purview. So in electric drive course we study this sort of aspects. Electric drives deals with this sort of aspects. First we deal with power converters, and then we deal with control system. First we will deal with 1, and this is 2. First we will deal with the power converter topologies, and then we'll go into the control system aspects of it, to the extent we can cover in this. So if you have any question, please tell me. In tomorrow's class, I will tell you the books, etc., all those aspects. Books means one book only I will ask you to read. But anything else you want to ask me now, just 2-3 minutes, you can ask me. Hello? Yes. Mr. Parth? Hello, who is his name? Parth.
Hello. Hello.
Hello. Anything understandable what I said? Is it okay, clear, or
Yes, sir.
anything you want to comment or anything?
No, sir.
Okay, then I am stopping here. In tomorrow's class, I will tell you about the book. If you want to follow, you can follow. Okay, I'm leaving now. Thank you very much. Okay.